A tank initially containing 10 gallons of water with 2 pounds of salt. Water with 1.5 gallons per minute enters a tank at a rate of 3 gallons per minute, and a well-stirred mixture leaves the tank at 4 gallons per minute. Okay? Ooh. Interesting. So we're actually losing volume. Assume that the amount of salt, x of t in pounds per mass in the tank can be modeled as. Okay. So we don't have to worry about like balancing the volume. They already gave us this equation. Be like, magic, here's the equation. We're like, oh, okay, yeah, okay. What is the maximum amount of salt present in the tank? Okay, so we're going to, from 0 to less than t, less than or equal to 10. Okay, so we'll test for 0 and 10, which are the endpoints. And then we'll test for the critical point, which we'll find using a derivative, setting it equal to 0. Maximum min. Okay, so x prime of t equals, so it'll be 1.5 times, this will be, you can view this as a chain rule. So this would be 10 minus t to the first. 1 goes down here. Oh, sorry. 1 goes down there. You get 0. This becomes then 1. And you multiply by the derivative of the interior, which will be negative 1, because the derivative of negative t will be negative 1. And so what we're left with here is negative 1 minus 0.0013. Okay, probably going to be a calculator problem at this point. Times 4 times 10 minus t to the third. That's a power rule. Then we have taken into account the chain rule. And then we will set this equal to 0. So what I'm going to do then is, we got negatives there. I'm going to rewrite this, 0.013 times 4 times 10 minus t cubed equals 1.5. Yep, because I took the 1.5, moved it over to the other side. And then, this is going to be calculator. So we'll have 10 minus t quantity cubed equals 1.5 over 0.0013 times 4. Okay. 0.0013 times 4. 0.0013 times 4. We'll quantify that. Is it 1.5? 1.5 divided by. Okay, check real quick. 1.5. Okay, let's see what the answer is. Bum, bum, bum. Oh, Wolfram, how I love you. 288. Okay, but then we're going to have to cube root that. Actually, I'll just write it down first. Equals 288. 10 minus t equals 288 cube rooted, which equals, and the way I do cube roots is to the 1/3 power, to the 1 divided by 3. Check to make sure it writes it out correctly. Yep, 6.6. Then we'll do 10 minus 6.6. 3.39. 3.39. T equals 3.39. Okay, so at t equals 3.39, we have a maximum or minimum. So what we're going to do then is plug that back into the equation. So we're going to do 1.5, 10 minus t. Quantity. 1.5 of 10 minus x. I'm going to write it as x here just to get the equation down. Minus 0.0013 times probably 10 minus t to the 4th. Yeah, that's actually the whole thing. 0.00, 0.00. Okay, and then we had, let's see here. If we do times 0, we have 2, which they gave us. Excellent. That's actually really kind of cool. Okay. Then we'll plug in 10 to see what happens. So we got probably 0, which is interesting. Because it should never actually go to 0 if it's warm. Maybe it just runs out of water. Good call. Good call. Okay, so then we have a value of 3.39. 3.39. Okay, remember that? Remember that? You guys got it? I'm relying on you here. Don't fail me. Oh, my highlighting skills are terrible. 3.39? 3.39. Okay, I'll check it again. 3.39. Okay. 3.39. Niner. And we have 7.43. 7.43. Oh. 7.43 pounds, and I guess mass. Okay. So what we just discovered was at time t equals 0, we had 2, which they told us is also conveniently true. At 10, we had 0. So it's a 10-gallon tank. It's losing a gallon per minute. Therefore, after 10 minutes, it's 0, which is fine. And then we took the derivative, set it equal to 0, solved, and we found that a min or maximum happened at 3.39. After plugging in the initial and the final, we found that the initial and final were both lower than the point that we found, which is 7.433. Well, at time 3.39 minutes, which gave us 7.43 pounds of salt in the tank. And that's how we would solve this sort of optimization problem. So general, I guess, procedure for optimization problem, you have an equation. Or if you don't have an equation, you have to make one. But this time we were given one. Take the derivative, set it equal to 0, and then find out that value of t or x or whatnot. Plug that value of x or t back into your original equation and compare the number you get by plugging in that critical point to the endpoints to verify if it's a minimum or maximum. And that's the way I like to do these sort of optimization problems. Thank you much.